Hello, this is Brenda Wingard-Haynes, and this is Chem 207. And these are video/audio files to accompany Unit 5, which is Energy, Equilibrium, Rates of Reaction, and Le Chatelier's Principle. Now, just as a disqualifier, I'm doing this in my house, along with my 3 dogs and 2 cats, so you might hear them in the background. The other thing is when I do this and upload them into either the Google Drive or YouTube, the files get blurry. So you might wish to have the lecture notes with the footer Spring 2018 in front of you, either blank, or I will upload the notes that I used as I made the videos for you to follow along. Either way. Also, there should be some videos from YouTube on the general topics to go along with what I put in these, what I'll call whiteboard app presentations. Okay, with that, let's go ahead and get going. Unit 5 is a particularly useful collection of information for people who go on to biochemistry, because the issue of energy, equilibrium, rates of reaction, Le Chatelier's principle are all drivers that go into the consideration of whether a reaction goes forward. Okay, so you need to remember that delta means heat. And remember also that the law of conservation of matter means that matter is neither created nor destroyed. So how about if I just say it's conserved? Well, in the same manner, energy is also conserved, according to the law of conservation of energy. And in order to do this, you have to define the system and the surroundings. So if you have a generic reaction, A plus B goes to C plus D, in general, you can think of the reactants as the system, and everything else equals the surroundings. Okay, so I like to use a campfire because most people, most of the time, have experienced a campfire. So the combustion of the wood is the reactants, and that is the system. And everything else is the surroundings. Okay? So if heat is lost from the system, that means it has to be gained by the surroundings. And so when we talk about heat, it's always in terms of the reactants. So the reactants will lose the heat, and this is called an exothermic reaction. Now, how do you know an exothermic reaction when you see it? How does it feel to you? Well, it feels warm, just like the campfire, because the heat is being lost from here, lost from the system, and gained by the surroundings. Okay, so in general, an exothermic reaction will show the delta sign or heat on the right-hand side because it is going into the surroundings. Page 2. You can also see a specific heat component. Okay, so kilojoules, kilocalorie, calorie, joules. Anytime you see something with a joule, a calorie, a kcal, a kilojoule, that's telling you that that's heat. So when you see heat on this side of the equation, that's telling you that the heat is produced. If it's produced, it's going into the surroundings, which means that it's lost from the system and it's exothermic. Another way is if you see a delta H equals enthalpy, and enthalpy means heat of reaction. Okay, so the heat of reaction is going to be a negative, so sorry, that's a typo in the notes. And oftentimes you see tables and tables of thermodynamic data where you have delta H listed. So all those are three different ways that you can recognize exothermic reactions when you see one. You see a delta sign on the right, you see a heat component on the right, or you see a delta H that is negative. Okay, so now you can also have the system gain heat. Gaining is a plus. It's taken into the system. And these are called endothermic reactions. Now, how do these feel to us? They feel cool because they are removing heat from the surroundings. So we feel cool. This is how a refrigerator works. This is how a air conditioner works. It removes heat from the surroundings. Now, what you'll see is the heat or the delta. You can also see it written over the arrow. That means heat is put into it. Or you can see an actual heat value. Again, calories, kilocalories, joules, kilojoules, they all mean heat. Or you can see delta H data in a table, or it's given in the equation, and it is some kind of calories per mole or kilocalories per gram or some such thing that has some rendition of calories or joules will tell you that that's a heat value. Okay? Now you can convert enthalpy to cals per mole or kcals per mole. You just find the molar mass here or the molar mass there, or you can convert to joules. You can do converting with this just like everything else. Now, if enthalpy is delta H and it's exothermic, it will be negative. And if it's endothermic, the delta H is positive. Well, the proverbial question is, why do we care? Well, in general, but not always, exothermic reactions tend to be spontaneous as written. And what this means is that the reactions will tend to want to go forward. So a favorable enthalpy in general is negative. An unfavorable enthalpy in general is positive. The second law of thermodynamics has to do with entropy. And entropy is a measure of randomness or chaos. And you can think about this. If I took a deck of cards and I flicked it across the room or onto the floor or something like that, would it land in a nice, neat little pile, or would it scatter? Or another analogy, if you're doing the laundry, does the laundry come out of the dryer, fold itself, and put itself away? Well, no, not at all. So a favorable entropy is one that is increasing. Entropy is delta S. Okay? So for example, if I want to melt ice cubes, I have to put heat into it. That enthalpy will be positive, and that is not favorable. On the other hand, the entropy is going from an orderly solid to a disorderly liquid, and the favorable entropy is positive. Well, which is it? This is not favorable. This is favorable. Which is it? Well, it depends. It depends on something that we call Gibbs free energy, which is a combination of enthalpy and entropy. And we're going to talk about that in just a minute. If I look at this reaction, okay, these are all going to be gases. Gas, 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 gas. So you look at the heat over here, and the enthalpy is negative, and that is favorable. The entropy is going from 6 moles of gas to 7 moles of gas. So the entropy is increasing, and that's favorable. So would this reaction tend to go forward? Well, yeah. This reaction would tend to go forward. We don't really need to calculate delta G because we know by inspection that it's going to be favorable. On this one, we are going from Well, we have to put some heat in there. Okay, so we're going to put the heat over on the left. That enthalpy is positive, and that is not favorable. Not favorable. On the other hand, we're going from 2 substances to 1, or 3 moles to 1 mole. So our entropy is declining. It is not favorable. So both of these are no, and we don't need to go to Gibbs free energy to calculate whether this is going to be favorable as written. We know this is not going to be favorable as written. It's just not, because both components are not favorable. So overall, when are reactions favorable? Well, it has to be a combination of both enthalpy and entropy, and we calculate that through Gibbs free energy, which we will look at the next segment.